Hello and welcome back to the Code Athlete. In this video we'll have a go at the problem D of Kickstart Round A 2022. It's called Interesting Integers. If you want to see videos to the first three problems, have a look at other videos. I've already published them. I'll probably put them all in the playlist. And on another note, tomorrow starts Google Code Jam qualification round, which I will record. There's a very generous time limit of 27 hours. I will try to do all 5 problems in one go. Hopefully it takes me around 3 to 4 hours. And I will upload that video directly after the 27-hour limit is finished. Of course not earlier, because otherwise I would cheat, you would cheat if you see that video during the competition. So I will avoid that by setting the upload directly after qualification round. So if you want to compare your solutions, I hope you take part. It's really fun. And if you want to compare your solutions to mine, have a look at that video or get some hints on how to solve the other problems or how the thought process could be to develop your own solution, and just keep practicing for the upcoming rounds 1 and 2 and possibly even 3. Yes, but now we'll just dive into the probably most complicated problem of those 4. But if you've seen my last video on the palindrome free strings, I really butchered that one up. Yeah, if this is even harder, you can see I'm quite out of practice. It might take me some while. You can see the video length already. Okay, so the problem is, let us call an integer interesting if the product of its digits is divisible by the sum of its digits. Okay, you are given 2 integers a and b. Find the number of interesting integers between a and b, both inclusive. So we're given an interval, we're given a property of interesting digits, and we have to find the number of interesting digits inside our interval. Okay, let's just look at the examples. So 1 to 9 seems to be all interesting, and that's quite clear because the sum of the digits is just the 1 digit, and the product of the digits is also this digit, and they're of course divisible by each other. 91 to 99, we have a product which is always 9 times n digits, so 9 times k. And the sum is 9 plus k. And if 9 plus k divides 9 times k, let's already start directly with the analysis and check why this can't be the case. Is it always that the sum has to divide the product, or can it be both ways? If the product of its digits is divisible by the sum of its digits. So if 9 plus k divides 9 times k, for which k? And we were given that it's between 1 and 9, because the interval was from 91 to 99. So if 3 is not a divisor of k, then this number is not divisible by 3. That means all the factors we have in here need to be all in k. So we have from 3 doesn't divide k, it follows that 9 plus k needs to divide k, because it can't have factors of 9. And that's clearly contradiction, because this number is bigger than this one. So it can never divide the right hand side. So it follows that 3 has to divide k, and we can just look at those cases, 9 plus k and 9k. So cases where 3 divides k, it's just 3, 6, and 9. For 3 we have 3, 6, 9. We have 12, 15, 18. And here we have 27. 27 times 2 is 54. Plus 27 is 81. Yes. You can see here is a factor of 4, which we can't find in 27. Here's a factor of 5, which we can't find in 54. And here's a factor of 2, which we can't find in 81. So yeah, indeed the correct solution is 0 here. Not sure if we've learned anything yet about this problem. Actually, this might be quite interesting because we get a feeling of how many there are. It seems to be that in 500 to 1000 there are 176, so yeah, around 30% even. So quite a lot of these numbers. How large can A and B be? 10 to the power of 12. That means already that we can't iterate over these numbers and do something in constant time. We need to be even smarter than that. Because simply iterating over the numbers from 1 to 10 to the power of 12 would, even if we just say basically now program hello to the numbers just by putting them into a variable, for example, and just iterate over this list. With this very simple operation, this would take too long, because 10 to the power of 9 would take 1 second. That means in the worst case here, 10 to the power of 12 would take 1000 seconds for just one sample, and we have to do 100 samples in 20 seconds. So yeah, we can't iterate over this. That's actually quite interesting. Means there needs to be a solution which directly looks at A and B and does something smart. We can do prime factorization quite fast of these numbers, A and B. You usually do this by pre-computing the list of primes to 10 to the power of 6 in this case. Because if you want to check if a number A, for example, and produce its prime factorization, you just need to check all the factors up to square root of A, which is square root of 10 to the power of 12, which is 10 to the power of 6. If we can't find any factors up to this size, then it means A itself is a prime. Yes. So we can compute quite efficiently the prime factorization of A and B. And because we're talking about the digits, let's actually write the number as digits. So number n is basically in the digit representation ai times 10 to the power of I. And this is a digit at the ith position, which is from 0 to 9, of course. And the sum of digits of n is then just the sum of ai. And the product of digits is then just the product of ai. And if the sum ai divides the product of ai, can't really see a cool relation here. I'm also now thinking it's really we only are looking at the digits, or basically this is a set of digits ai for a specific size, for a specific length, So reordering these in our numbers still gives us the same. So if we reorder numbers in the digits in the number n, then we have a different number n, which the same sums and products are revealed, and therefore the divisibility operation results in the same true or false statement. Interesting or uninteresting statement. Maybe the question is, even if we go up to the numbers 10 to the power of 12, how many different sets are there actually? And that's probably much less, but how much less? Maybe not enough. But we could pre-compute this actually. So if we get this down to, let's say, 10 seconds to pre-compute, but it doesn't fit into memory, yes. Well, we could pre-compute large intervals in some tree structure. And then for smaller intervals, we can compute it live. It will be much faster. So if we have the numbers run to 9, yeah, so there's some, I won't go into much detail into this, how to compute the number of possible sets, different sets we can have. But you can say, for example, we have 12 different slots if we have 12 digits. And if we have a given set of digits, we can sort them and put them here in. So for example, sorted, we have 1 0, but then 3 1s maybe, no 2, but 2 3s, and so on. We could put like separators here, and we would put 2 separators in this place because we are skipping basically the 2s, there are 0 2s. And this results in putting, because we have the digits 0 to 9, we are putting 8 separators in between. Is correct. If we go from 0 to 1, we would put 1 separator. So if we go from 0 to 9, we actually put 9 separators because we have 10 digits. So we put 9 separators between these 12 digits, and we can reorder them in any way. So if I give you some combination of separators and boxes, this corresponds to exactly one set where we put here the 0, then we have no 1s, no 2s, then we have 3 3s here. So this representation would correspond to this set. And basically, and one set can translate directly into one of these combinations or permutations. This is basically 9 separators plus 12 boxes. So in total, 21 objects, which we need to reorder in some way. We have 9 separators, which we need to find. So this is a binomial coefficient for this. And yeah, I can actually plug it in my calculator to see how big this number is. Oh, and it's actually it's surprisingly slow. I thought it would be much bigger, but it's just roughly 293 94,000. So not exactly, a little bit less actually, but that's all the permutations of digits we have for a 12-digit number. Actually, we only have 11 digits, I'm just realizing. So for 11 digits, it's actually just 20 over, again, 9. Yes. So this would be, again, I think maybe only 20,000 or so. No, still 168,000. But not that much. So this is a list we definitely could put into memory. And also save if it's interesting or not. And then we just need to compute for a given interval how many different types of numbers we have in here. But it's still, that part is still not clear. It's interesting that we can pre-compute this list of digits and if it's interesting or not. But how do we use this to construct the counts for our intervals? So I'm just wondering why I got the impression this number would be much larger. So the way you compute this is actually 20 times 19 times 18. Oh yeah, so just 9 times. So this divided by 9 times 8 times 7 and so on. So this numerator is smaller than 20 to the power of 9. And this one is probably bigger than 3 to the power of 9. Or it's definitely bigger than 2 to the power of 9. So dividing by this, we have actually that this whole number is smaller than 10 to the power of 9, yes. And it's actually roughly only 10 to the power of 8. Oh, it's now again I'm confused. It's much smaller than 10 to the power of 9. What is this number here? 9 faculty. So that's more like 3 times 10 to the power of 5. It's 2 to the power of 9 times 10 to the power of 9, and that's roughly 2 to the power of 9 is 512 divided by 3 times 10 to the 9th divided by 10 to the 5th is 10 to the 4th. This is roughly 107. 1.7 million. So again, this estimation must be also quite bad. It's about factor 670 wrong here. Okay, so it's hard to estimate these numbers. I'm really surprised that it's so small, but this really might help us solve this problem. It's always good to check if you've got a wrong impression about something. So I had a wrong impression about this binomial coefficient. I've almost missed it too early. So I was actually lucky just grabbing my calculator and checking this number, because otherwise I would have thought this is not feasible. And if this is the only solution, I'm happy I found it now. Yeah, so, but we still haven't solved completely the problem. So, for example, for this last interval, 501 to 1000, we need to somehow okay, actually I guess no, yeah, right, because we included the zeros, we actually can have less digits, yes. So yeah, I think we can just put this into, we need to just split this up into smart intervals. So I guess one interval would be to take all the numbers with 500 starting. Because this effectively means we have 1, 5, and then we can put 2 digits of anything into it. And we need to have a lookup structure that says, okay, what is if we have, because we always count like 12, let's say we always count 11 digits. We actually need to do the case 12 digits, no, always 11 digits. Then we would include leading zeros here, because for the product, zeros don't work. Also, I guess all numbers with zeros we can directly ignore, yes. Because if we have a zero in the product, oh, but leading zeros? Yeah, but you should ignore zeros here, so this gets even smaller now. Because if we ignore 0, we have only 8 divisors. That means we are down to 19 over 8. And we will see how low we are now. What did I say? 19 over 8. Yeah. It's only 75,000 combinations now. Very interesting. And we somehow need to sort these. So that we can easily look for all the combinations where there's 1, 5, and 2 other digits. And then we have this interval, then we go from 600 to 699. And so on and so forth. If this number would not be 1000, but let's say 11,000, then we would do all these intervals up to 900 to 999. And now we would go from 1000 to 1099. we do that actually? Yes, I think so. Because we have an 81, yeah. Then like this. And then up to 9,000. And then we start by 10,000 and we go to 10,099 because that's actually the last one basically, before we skip to the next one. So, and if we can handle each of those in sublinear time, so maybe something like logarithmic between the start and end, I think we're good then, because in this direction we have only maximum of 9 blocks each, because we always increase the first digit from 1 to 9. And in this direction we have maximum because we always get one magnitude of order higher. So these are the hundreds, basically these are the thousands, these are the 10,000s. So this is at maximum because the maximum order magnitude of order difference between A and B is 12. So this is a maximum of 12. So we have 9 times 12 times something in hopefully logarithmic time here over the length of the interval. And that should be definitely fast enough if we can manage this. Now the problem is if we have these nice intervals where we have like given some digits of the 12 and then we have some digits which we can choose completely freely now, because I constructed those intervals all the same way in such that the last 3 or 2 digits can be chosen between any possible combination of 000 to 999. So for example, in this case here also the last 3 digits, usually this is last 2, last 3, and here would come last 4, but because the last number is in this example 11,000, we only take this interval smaller to the last 3. So actually I think this could go up to the highest order, then back down to the lowest order. So if this would be 11,111, we would do it like this, and then we would go from 11,000 to 11,099, and then we would go from 11,100 to 11,109, and then we would just do the last 2 digits by themselves. So this again could go 12 down, so it's 24 times 9, but still times something the sublinear time we need to do for one of these intervals. So that's the special way I've constructed them, that the last 3 are free. So and I think the smaller this one gets, so for example in these cases where we only have the last digit varying from 0 to 9 or only the last 2, these we can afford to actually enumerate and check all of those separately. And our checks are quite fast now because we can just look the pre-computed list up. And only for the bigger intervals we need to do, it's getting heavier basically to compute this, but we could do this offline and save those results for those bigger intervals. But still, even if we do it offline, we can't afford to just iterate, because 10 to the power of 12 iteration in total is not feasible, even if we just do one test case basically. Like I said, it takes 1,000 seconds and we only have 20 in total for all 100 test cases. But it basically means we could spend quite some time on these. Still needs to be sublinear. And way to go here is probably to count all the different combinations we have for those, because selecting 3 digits between 0 and 9 or basically we've concluded that zeros are not allowed, so just between 1 and 9, or selecting k digits between 1 and 9, we get this formula which is k blocks plus 8 separators, because we have 9 digits. We need to find the position of the 8 separators, so this is the total formula. And this is fine now for k up to 12 or 13 even. So we go through all of these sets for, let's say, 3 digits. And then we need to count the frequency of the occurrence. So for example, the selection 1, 2, 3 has an occurrence count of 6 because it's 3 different digits and I can rearrange them in 6 different types. But the 1, 2, 2, for example, has only an occurrence count of 3 because I have 3 positions where I can put the 1, and then the other 2's need to be filled in. And if we have 3 of the same digits, there's only the 1 occurrence. So for every k, we can compute this list of possible combinations, and for each of these combinations we can also compute how often they occur. And then if we ask for a specific interval, we can just iterate over this sublist, multiply by the counts. Yeah, and I think that should be fine. I would try to start implement this now, I think. I'm still not 100% sure in which data structure I would put this, if it's a dictionary where the keys are actually sets and the values are the Boolean value of being either okay or not okay. Or is that actually slower than to just compute the product and the sum of the 12 digits and check the divisibility? I think that might be pretty close to being the same efficiency, so I'm not sure if I want to pre-compute this. We'll see. I think we'll improve upon this in the end. So reading the input, we just read in the start and the end. And then we write a function which just counts. Count interesting. And the first thing we do is split this interval up into our good intervals, and then this function will call itself recursively. And we can then inside this function check if A and B have the special property of the last n digits being basically free from 0 to 9. call a special function which does the computation we just discussed. Let's actually do this check first. In which case are A and B nice? It's the case where B minus A is all 9s, right? That's basically it. Yes. If B minus A is all 9s and at the same time A has only zeros in the end digits. Yes. We will write an extra function for this nice interval. And if it's not a nice interval, we need to split it. Compute split of A and B. We return count interestings of split 0 to split 1 plus the count interestings from split 1 plus 1 to split 2. Actually, split can just be the middle. Let's do it like this. And then we go from A to S and from S plus 1, because it's always inclusive, to B. Yes, and in the case where we have a nice interval, we do this complex stuff down here. So let's first compute the function that we have a nice interval. And I'm thinking now if it's maybe the simplest to use the string to integer function here and do string manipulation. If I would know how to do that. E to RS. And let's do it like this directly. E to R stands, I think, for integer to ASCII. Something like this, and this produces actually a char pointer, but I hope that the string class directly can convert this. By the way, this is just a shortcut here I use. see I'm using namespace SD, so why is A to A not working? Oh yes, so there's a toString function actually. Yes, much better. And we also have to look at the A, which has to have ending zeros. So if it's not all nines, we return false, it's not nice. If it's all nines, then we need to check that the string in A is all zeros. So from I plus, need to compute the offset. A dot size minus div dot size. Yes, I think that's right. And this, if this is not equal to 0, we again return false. And otherwise we return true. We need to take AS, the string version of our integer. Now, computing the split. What is our strategy to generate those splits? I need to find the next largest number. So if the last digit is not 0, then I need to go up just by 1, right? Yeah. So again, let's take the string version of our number. Return actually A, because then we here go from A to A and then from A plus 1 to B. Why is this not happy? Oh, it's happy now. So if we have some ending zeros, we should check how big the difference is, right? I think we need to do this again. Because the difference describes how much at most we can go up in terms of digits. So let's try to compute a delta for the split, and we return a plus delta. And we do this inside a while loop, while, let's say, a plus delta smaller or equal to b. Let's also use a counter maybe for this while loop. Because this is the number of last digits we can actually afford to the counter gives us the number of last digits we can choose freely. Yes, I think that's right. So here with counter equal to 0, we look at the last digit. If it's not 0, it means we can't even choose that one freely. And we break. But if we can choose it freely, actually just we control the breaking inside here. If we can choose it freely, we can check if a plus power of 10 to the power of counter plus 1, I guess. Because for counter equals 0, we look at the last digit. If it's 0, we can choose the last digit freely. That means our delta is 10. No, it's actually just 9, from 0 to 9, because it's inclusive. So this is our delta. 10 to the power of 1 is 10, minus 1 is 9. And if this is smaller or equal to b, then we are good. We can increase the counter and let's directly turn the split value here. New split is this one here. Which we can then use in the check. And then if this is not smaller or equal to b, we can actually break and use the previous one. Yes, so that will compute us a split. And we can print this now and check if this actually gives already the correct results. So not the correct results, of course, but we can sanity check if it gives us the intervals we want. We have, for example, already computed this. Yeah, it's using my, oh, sorry. Oh yeah, and in the calc function we of course should call our function. I'm a bit worried because it doesn't read the other test case, so I think I'm suppressing a segmentation fault here. Yes, okay. Good or not good? Segmentation fault. Yeah, it goes into an infinite loop, okay. So it never breaks here for some example, even though we've increased the counter. This counter needs to be smaller than as.size, no? Because we can't go below 0 here. Let's have a look at the split output. Split of, oh, so it will produce the split. Well, if A is equal to B, it surely must be a nice interval. If A is equal to B, diff is 0. Yeah, I think we need to handle this separately. Okay, now it goes through all the 4 test cases. Yeah, and actually have a look at the last example where it's from 501 to 1000. It's not a nice interval. It splits and it computes 501 a split, then 502. That is all okay. And from 510 it should go to 519. Nice. Now it goes in 10 increments up to 600. 600,000 is not a nice interval. It goes up to 699. Now it goes in hundreds. And here it says 900 to 1000 is not a nice interval. It goes to 999. And then we have the last interval from 1000 to 1000 again. So yeah, let's remove some of the logging again. Because the splitting works, I think now. It looked quite good to me. Now we can print only the intervals that we actually need to compute. And those look all fine. That's good. Now we need to compute the number of last digits that we want to have freedom over. So we have a prefix. Yeah, let's compute this. So again, we use a string representation of diff because this gives us the length of the we should again use the extra special case if a equal to b, return is feature string a, and if it's not a equal to b, then to string we have prefix, and let's say then as is to string a, prefix is as dot substring starting from 0, and the length is as dot size minus diff dot size. Number of 3 digits is just diff dot size. Yes. If the prefix contains any zeros, we've already lost. We can do this as a pre-check, I would say. Yes, I would do this. And a and b are not 1, so we can't have this only one stuff here. So if prefix contains 0, we can just return 0, because none of them, because the product then will always have b0 and the sum will be always bigger than 0, because a and b are strictly larger than 1, so there needs to be some leading digit which is non-zero, and that means the sum is bigger than 0. So yeah, now we have a valid prefix. Now we can iterate over all the possible combinations for the 3 digits. Check if it's interesting. And yes, we will compute the two this interesting function, I think, on a string base, because here we will naturally have strings. So can we do this over? Yeah, I explained this with the separators and the boxes where we fill in the digits. I will use exactly this mechanism to construct my sets. So I will have separators here. It's a bool array actually only. It has the size of number 3 digits plus 8. Because we have 8 separators. Yes. And we will initialize those to all 0. or false, because it's a Boolean array, but we will initialize the last 8 separators. Can't spell. The last 8 of these will be set to true, because we always need 8 separators, and the other ones are false. And now there's the next permutation call, right? So do something. Let's for now just print us these separators, while next permutation of separators. This will just reorder them. And I think I need to use the iterator start and end. Let's just write the isInteresting function for now. We have a sum and we have a product. Let's initialize the product with 1 and the sum with 0. Go over the digits. Sum digit is AI minus 0 char. So we can construct the sum and construct the product. Return product modulo sum equal to 0. That means the product is divisible by 0. Now that I'm thinking of it, is actually 0 divisible by the sum? Is that allowed? I have an example right here. There are 5 interesting integers between 451 and 461. Again, here no zeros. Oh no, it says 460 is okay. So so I've got this wrong. Zeros are indeed okay. So this check is actually okay, and I have to check other things now. I mean, the splits are still all valid. That's all good. That's now all good. I can't use this anymore. Actually, if prefix contains a 0, all of them are good. So in this case, I can actually return b minus a plus 1. Yes. Yes. Interesting, okay. Let's see if the permutation of separators works. So here, for example, you can see we have 1, 2. So this is, for example, the case where we have 2 free digits. Then 1, 2, 3, 4, 5, 6, 7, 8 ones. And here you can see how the zeros propagating to the back, and it really captures all the possible combinations down to this. And I think here's a new case starting. Here's again a new case starting. Actually, let me check this, that this is the case. Yes, so here it finishes where the zeros are in the end, and then we start again. And yeah, so we really get all the possible combinations here. Now from this we need to construct the digits. And we need to compute how many possible permutations there are for this. And because we have to take care of the 0 now, we have 9 separators and 10 digits from 0 to 1. 9. So yeah, that just happened. How are we going to do this? Construct the post string. Need to initialize an answer. I think I have a choose function which computes the number of combinations we have from taking A out of B. So yes. So we will now construct the post string, and we will keep track of the number of cursory digits we have left, and we will count the number of permutations we have by going through our separators, adding the digits we've to our post string, updating the permutations by multiplying with taking from the current 3 digits, which we will decrease over time, and the ones we need to place. Place digits. This will be multiplied to current permutations in a for loop where we go over our separators. If we have a separator, then we are 1 digit further and we reset the count to 0. But before we do this, we need to update. Yes. So let's add actually a +1 here. And if I is equal to separators dot size, or we have a separator. So this actually adds a virtual separator in the end, so that we do our update routine. And if it's not a separator, we just increase the count by 1. Now, And this is count. The number of digits we now have to put in to our post string. Yes, and we have less 3 digits now. And let's log this. We have the separators logged, so we can look at the generated post string. We can look at the permutations we need. And now the update rule to our answer is just permutations times is this actually interesting. And the string we are looking at is our prefix concatenated with our postfix. And I think this should actually be already the solution. Assertion failed. But the number of curve-free digits is at maximum 12. And here it says it can go up to 61. So that we get this error means that we put some wrong values in here. So I have this assertion inserted so that we make sure that we don't put like 60 or 100 over 12, because with long values those numbers get pretty large. But we are in a regime where these... Oh, actually, you know what? This must be a... No, this should be right. Let's just log what we actually put into this. But I'm also a bit... Why is actually 1, 2, and 3 doing nothing? It's a bit weird, isn't it? Because those are actually just iterating over the last digit here, the last digit here, and the last digit here. Yes, that's why they're fine. Okay. That's why we already get the result for those. Yeah, this looks strangely wrong, right? We shouldn't set count to 0 and then directly increase it. That's all the reason we got the trouble. Ooh, and we got even the right result. let's just see how this works. For example, in this case, we have these separators, and we get in the end count of 1. Post string is 89. We have 2 permutations. Yes, 8, 9, 9, 8. So yeah, let's maybe delete these 2 lines again. We get more interesting post strings with 3 digits. I think we should get those, right? We had these intervals from... No, we don't get those? Is it always only 2? But here, for example, this is interesting. We have the post with 2 values and 2 permutations, and here the post is 44, and it's just 1 permutation because we can't switch them around and expect them to generate a new number. A bit disappointed that we didn't have the 3. Let's put a new test case in so we can see the 3 digit version. So for example, from 1000 to 2999. And in this case, yeah, we have, for example, here 788, which is just 3 combinations as we discussed, but 789 is 6 combinations. So that actually works. And the separators corresponds to the post, right? So we have here 0, 1, 2, 3, 4, 5, 6, 7, 1, 7, 8, 1, 8, 1, 9. Here we have 2 8s. Yeah. So this translation into the post string works, the permutations work, and now the only issue might be that this is too slow. But let's have a look again at our algorithm. So this should split, and according to the computation here, we would have at most 9 times 12 times 2, because we go 12 orders of magnitude up, 12 orders of magnitude down, and for each magnitude we have at most 9 leading digits that need to change. So this interval split would result in at most 9 times 24 callings of this function, where we go into this here part here, and then we do even some shortcuts here and here, but we can ignore them. The most important thing is how often do we go through this loop, and then inside this loop how often do we go through this loop. I think this function is pretty cheap. It's probably logarithmic or so, and we only put numbers up to 12 in here, so this is pretty small to compute this product. This overall, because count in sum smaller or equal to number of 3 digits, so this corresponds directly to the number of 3 digits, which also is the loop size of this one here. So I think the outer loop is the most interesting one, and like I said, this should be at most number of 3 digits, which is at most 12 plus 9, so 12 plus 9 is 21 over 9, all the 9 possibilities for the separator, so it's 200,000 at most. Times this inner loop, which is at most 24 or so, 21 again, this size, or 22 in this case. Yeah, so we should be at around 4 million or so of these inner things, 4 million operations, which is 0.004 seconds for one test case. So I'm pretty sure this should be fast enough, but we'll have to see. And I'm pretty sure it's right. but also that we have to see. Now I'll just use this test case and assume that my solution is correct, and I can just plug it in here. Actually, in this, this is actually a thing where we can even write the test case with this large number. So the most extreme is from 1 to 1 with 12 zeros. Yes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And our program tells us how long this will take. Of course, with the printing, it's pretty slow. It's interesting to see how it goes through all the permutations. And we actually exceed the time limit. That's a bit worrying because I have no real clue why that might be the case. The log number of combinations we have here. These are just annoying. So these now, I think that works. Well, it's not bad really. Well, but still we are at 1.4 seconds. We have here 167,960. Yeah, this is this number where we have 8 free digits. Yeah, so here the last 8 free. Oh, because I have to multiply the, what did I say? No, 0.004 times this grid here, 24 times 9. What did we go? Where did we go there? So yeah, I think 11 free digits is actually the most, like we said. So that's why we see at most here 167,960. And this we can have at most for 9 different digits. Is this actually correct? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, and then 9 times we have this one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So again, at most 9 times here. And then the previous one. And this we have at most 24 times. Yeah, now I'm at 36 milliseconds actually, or then this is still too slow. Well, I guess now it might actually be because of this function here. And this function. Yeah, this function adds another factor of 20, right? Oh, and now I'm at 0.7 seconds in theory. And now we're only a factor 2 away of this. But yeah, I think we just need to get like a factor of 10 faster. So now it's really just point for optimization. Is this choose function actually memorizing results? That could speed up a bit. But really this construction is suboptimal. Or maybe I should save some intervals. That could actually speed up quite a bit. So for example, if I say if the number of 3 digits is larger than 10, or 9, yeah, there might be some. Yeah, so you make a dictionary where the keys are A and B, and the values are just this. And now we just put it in here. If make pair, if mem results dot count, make pair AB, then return mem results of make pair AB. Yes, and if we have done all the work, we actually will save this result if it's worth it. So if the number of 3 digits is basically large. Number of 3 digits, let's say, is bigger than 8. Mem results make pair of AB equal to answer. And let's us print the size of mem results to see how big it gets. And now I will actually add this test case a second time to see how big the speed up is here. And this should be the correct result. I'll change this to 7, yes. So the first test case should be the same speed. Oh, actually it also got faster. Not really sure how that is possible. Maybe it's reusing some of the ones for the first. Not really sure. And here we can see that it's always saving the results. And here we're skipping over a lot of the computation and cutting it down quite significantly. I'm just worrying if I put this too low, it might save quite a lot of stuff here. Because if we have 5 3 digits, that means we have 6 non-3 digits. And those can have quite a big, yeah, so 6 non-3 digits. So that would be already 1 million. Different pairs that might be saved here. So I'm not 100% sure if you can even save a lot of computation. We'll put this at 7. Not sure if this is fast enough. I mean, when there are 11 free digits. Now, if there are 10 free digits, then there's only one non-free digit, and we have only 10 different pairs here. And those might be actually reused. Oh, and it's now fast enough. Okay, so that actually worked. Yeah, and if we have 9 free digits, that means we have 2 blocked ones, which are already 100 pairs. We might not use all of them in the 100 test cases, but there's a good chance. Yeah, so the less free digits, the more different combinations we write into this dictionary, but on the other hand, the less speed we gain by using the answered ones. So the bigger ones are just more important and more likely to be reused. And I think that makes this work. But I think there can actually be done quite a lot of speed up. So you've probably seen here I've used a lot of this toString manipulation, but only in these functions that are really called only 50 times or so for one test case. So it's really not that big of a deal, because this nice interval just goes these 12 levels down and 12 levels up again, basically. So it's called basically 9 times 24 or so. So that's not a lot for the computer. And the same for the compute split. It's also computed very little. And then this function is, of course, used quite a lot. But I think it's also quite cheap. And then, yeah, I think the heavy lifting happens here, and I'm not sure if there could have been a good speed up. For example, it could be that there's an even smarter way to iterate over all these combinations. I'm not sure. Actually, I will have a look to the analysis with you together now, just to see what they propose to make it faster. Oh. This is much faster. So, okay, now immediately when I see this, of course, you have this relation. Let's say we count from 0 always to n. And if we want to have from a to b, we just count from 0 to b and subtract the number of interesting numbers from 0 to a. That's basically telling us this formula. And now the splitting can also be done much more interestingly. Yes, we can... yeah, this would have made things much easier. Because now we only need to compute this function, and for this one we can do the split quite easily. And we could save numbers here. think they do something very similar here, but it might be that they actually skipped over. They skipped directly over the. Oh no, I can't really see it now. Okay, so this is quite a long analysis, as you can see, and there's even a second method here. So, oh, this might be even the longest analysis any CodeJam or Kickstart problem I've seen. So yeah, I'm very happy that I solved this problem. I think it was quite hard. I'm not sure how long I'm recording already. Oh yeah, 1 hour 40 minutes. But taking together with the other videos, I think I would have solved this whole competition in, what's the time given for these? I think 3 hours. So we can have a look at the last place here, I guess. Place 200 or so. See when they've submitted stuff. It's not 2 hours. Hours. Yeah, I think it's 3 hours or 2.5. No, 3 hours. And here we have 3 hours, or is it even 4 hours? Yeah, it seems to be, or is it just that much of a penalty here? 6:20 and each penalty is 4 minutes, or what? It's 104 minutes penalty. Yeah, okay, so yeah, it's only 3 hours. Okay. Would have been a close one for me, but I think I did a little bit of talking for the videos, and if I would have concentrated a lot on the problem, I think I could have gotten full score maybe on this Kickstart. Sadly, it was in the night, that's why I decided to use it as practice for the upcoming CodeJam rounds. But yeah, I feel quite good prepared now. If you want to prepare yourself, look at past Kickstart problems, and if you get stuck, look for the video on my YouTube channel, and of course at my solutions and notes in my GitHub repo. And make sure to check out my qualification round results and my video for this. Compare your solutions. Leave a comment if you have any questions, if you have feedback for me. I tried to make the sound quality a bit better today. I hope it works. I'm always happy about every like and subscription I can get. I'm trying to build up this channel, so every help is greatly appreciated. I wish you best of luck for your participation in Google CodeJam and upcoming Google Kickstart rounds. Have a lot of fun problem solving, and see you next time. Bye!